Been good to record, Jeff, but oh well. So it's strong positive correlation. The data points are close to the line because R is close to 1. I will trust it to make predictions. So here's the thing. I kind of like this. Oh, some of you guys are going to hate this, but you remember in algebra, if you had a problem with a percentage, you had to make it a decimal? And in fact, in this class. But we created this damn function, right? We created that line at best fit that I haven't written down. We created this bad boy. So what are the inputs for this? What would I put in for x? What does x represent? Yeah, as a percent number, right? Not as a decimal number. So if you put 37.6 into this equation, you'll get a prediction for a state where 37.6% of its population has a bachelor's degree. And what do you get when you do that? If you plug 37.6 in, what do you predict for y? And if you compare it, of course, to Virginia, which actually does have 37.6% of its population with bachelor's degrees, you get 71,535. So that's pretty damn close. I mean, R was pretty close to 1, so I would expect predictions to be decently close. Try some other states out that will be further away or closer. You guys with me on this? You guys on it? Okay. Yes?
If you explain R and that your answer is like weak, strong, or moderately strong, or whatever, can you still say the data points are close? Like, say it's like 0.6 or 0.7. Can you still say that?
No.
Okay.
I mean, you could. That's why I'm going to give you one extreme or the other. So if R was 0.5, you'd say really weak positive correlation. The data points aren't really that close to the line, right? But they're better than nothing. So I'm going to give you either a really weak-ass problem where it's very clear what to say, or a really strong R like this, where it's really clear what to say. In the middle, you're like, what? Can I say that? Not really, but I'm definitely going to use the line to make predictions because it's better than just guessing the average income for all the states. Right? The line's going to give me something better than that, but it's still going to be pretty bad prediction. But just a little bit better than just guessing the average. I like it. I like it. So this last dude is just, the correct answer to this last guy is I don't know. Don't say no, don't say yes, because those are both wrong. I don't know. There seems to be currently a relationship. Does that mean that changing one causes the other one to change? That's a different test. So if I saw a connection between, people exercising versus their level of cholesterol. Does that mean if I make this person exercise more, their cholesterol will go down? I don't know, because there's other factors in everybody. Are you guys kind of with me on this? So correlation just says there's a relationship. I don't know if one causes the other one, or it's the other way around, or they both are caused by something else. I don't know. So what this... I always have to be careful when I tell people this because it makes you feel like, well, this is all shit. But obviously this isn't shit, but this is why this is stats 1. This is entry-level, beginning stuff. And then you start doing more analysis when you see something that's like, why is that? That's interesting. Let's do more analysis. Let's actually try to do an experiment and change something and see what's going to happen. Control for more variables, right? The difference in standard of living across states. I didn't control for that shit. So if you ever watched any Mythbusters, you've heard that statement before. Anybody ever watch Mythbusters? I know it's not as... I haven't even seen the new ones, but the new people, I have no idea. Adam and Jamie all the way, but the old ones are great. But they always will say, at some point, you got to control the variables. You hear that all the time in that show. Okay. Why or why not? Because this is just correlation. Correlation does not mean causation. This phrase has come under attack. And I understand because, just like think I railed against these last time. Blinkers on a car were a really good idea. It's just that some people don't use them correctly. Correlation is an excellent idea. It's just that some people don't use it correctly. Right? So the correlation does not imply causation. That doesn't mean that nothing causes anything else. It doesn't mean it just says, I don't know with this test. It's not kind of the right kind of test. All right. So let me think. I was considering this. I think I might do this. This might be good. We're going to have our last quiz. On Monday. I'm not going to give you a big-ass collection of data. It's going to be a relatively small problem. It's going to be one of these kind of problems.
Chapter 12?
Yes. It's going to be a correlation problem. So you're going to have to calculate R, calculate line of best fit, get the scatter plot and the line, come up and show. Okay. All right, so the rest of class. Now, let me give you this right now before I forget. I actually have the practice final printed out already. So I have an answer key for this a week from today. Oh, no way. I love that question. It's a good question. But no corrections for the final exam. I love the name of the final. That tells you.
When are we going to make the notes that we get to bring?
So next Wednesday is going to be devoted to review for the final exam. The next Wednesday we'll go through the entire formula sheet. So you can make a fresh one and we'll put all the formulas from the whole semester. I like to do that first because it kind of spurs people to go, I don't remember any of that shit. Let me ask, how the hell do you do that? All right. Okay. So, what we're about to get into is that section I skipped because it deals with a brand new distribution. So we've had normal distribution, and we've had binomial distribution, a uniform distribution, we had T distribution. So now we have a brand new one. And the idea with this, oh shit, oh, you guys know there's a quiz coming? Oh, did I bring those? No. That's right. So this is called chi-square. Gotta love that shit. It's not x squared. It's a Greek letter chi. It has relatively little to do with Dragon Ball Z, so I'm sorry. I'm gonna need you, I might need you later. So you pronounce this chi-square. So I want to tell you the name of it. I want to tell you we're about to get into a new one. But now I want to explore why the hell we need another frickin' distribution. So look back at our normal, the one we use the most, the normal distribution. What governs the shape of that distribution? For any given normal distribution, I could have a mean and a standard deviation. I know it looks like a bell, but what tells me if it's going to be skinny, fat? What tells me what the shape of it is going to be?
The size of the standard deviation.
The standard deviation, right? The standard deviation is really tiny, it's going to be really skinny. If the standard deviation is bigger, it's going to be fat. Whoa, right?
Oh, and the scale you use.
So again?
And the scale you use.
Yeah, if I'm using the same scale for all of it, it's going to be that. So for the normal curve, the standard deviation governs the shape. Right? And the actual things that are in the distribution are means, or either data values, means, or percentages. We've seen all three of those. So remember when we talked about, I could have this curve and it's like each point is one person I talk to and their age. Or I can have a curve, so that's mu. Or I can have a curve where each point is a group of so many people and that's mu x bar. And that's when the standard deviation changes. You've got to divide by the square root of n. So all this coming back. And then, of course, p's have the same kind of distribution. We use that in the confidence intervals and the hypothesis tests. So what this guy is for, these guys are for how do data values or means or percentages from samples, how are they distributed? One of the main things this guy does is talk about how standard deviations themselves are distributed. So one of the main describe how standard deviations themselves are distributed. So it should kind of make sense on one level immediately that it probably won't have this shape because the shape is governed by standard deviations, right? So I have one standard deviation for this picture. Well, now I'm going to get all the possible standard deviations and then plot them. Okay, now go with me. All right. So I'll tell you when I transition from concept to what we're going to actually have to do. We're still in concept. I'll tell you, right? So you remember for these guys, the z-score was this, or this, right? You guys, that looks familiar. Or if it's percentages, it looked like this. You guys with me? Yes, yes, yes. So if I did make these z-scores, the formula for the shape of this and what these values are these things. Right? It's actually just what the values are. Okay, I like it. So if we drew this, and I said probability z greater than 1.41 or something, and you all look that up, this picture is a picture of z-scores. They live on the normal curve. It didn't matter if that z-score would have come from means, would have come from percentages, whatever. So this new distribution, that's a lot of red, Jeff. This new distribution, let's investigate why it makes sense, what it looks like. So if I take a sample and take the standard deviation, one idea I had today that I thought I didn't really necessarily want to do is give everybody a whole bunch of data and you pick it and you get a standard deviation. We've done that already a lot. I don't want to do that to you again. But if I have a set of data, N149, just a huge set of data, and you take a sample, you take every possible sample, let's say of size 3. So you pick 3 numbers at a time. Get the standard deviation. You get another 3 numbers. You get the standard deviation. And another 3 numbers. You get the standard. And you plot those. Every time you get a new standard deviation, you plot it. What would that picture look like? It ends up looking like this. So there's going to be a big chunk of sample standard deviations that are all kind of clustered around. And then there could be does it make sense? If I take a certain sample, I could get a huge standard deviation for that sample. We've seen this happen. So if I have a sample, I could just happen to pick a bunch of numbers that are really far apart, and the standard deviation comes out way bigger than the real standard deviation is. Maybe. Is that going to happen a lot? No, and that's why this part of the picture makes sense. There are going to be some standard deviations that are stupid big, but not a lot of them. Most of them are going to be right here. Okay, I like it. I desperately, stay with me. Some of you guys are looking, I can see in your eyes. You're all like, why? This is almost too awesome. Okay. So we have several formulas that lead to a z-score that lives on this distribution. Is that cool? I can make a z-score. It doesn't really matter where it came from. I have a bunch of different formulas that all fall into this shape. The most fundamental way to calculate a chi-square score, those are what's going to fall in this shape, is this. Oh, let me see. I want to make sure everybody can see it. I hate this stupid thing. All right, come here. This poor little pen. Now what's really, really cool, let me see if you guys get why. The average value on this is n minus 1. The average chi-square score is n minus 1. And why does that make sense? What would S have to be so that this is n minus 1? What would S have to be so that this is n minus 1? So what's S squared divided by sigma squared have to be so that you end up with just n minus 1 here?
They need to be the same.
Okay, good. They have to equal 1, so S would have to equal sigma. And isn't that what should happen the most? Obviously not always, yes.
Couldn't S equal sigma times -1?
Of course not.
'Cause then
S can't be negative.
Oh, I see.
Yeah. Right, standard deviation is a distance. It can't be negative. I like it, I like it. But I see where you're going with that, but no, mathematically, no. If you guys are at all with me. But what if I take a sample and get a standard deviation for that sample, isn't my best guess that that's the real standard deviation? That's my best guess. Are you guys, we've done this before. What do I use when I don't know sigma? We use S. I don't just randomly pick a number because S is my best guess. It should be close to sigma if I picked a relatively good random sample, right? Will it definitely be? No, that's why you have this big-ass distribution of all the freaking things you could get. But what should the expected value be? It should equal the actual real standard deviation. That should be what I expect on average. But, obviously for anything, I could get a really huge one, a really small one. If I happen to pick everybody who's the same age, I'm going to get S equal to 0. And why is it so small? Because there's only one way to do that. I pick all the same data point, right? All right. This is still all concept. And not all of this concept is necessary to do the problems we're going to do. And I don't seem to care about that. Because concept's more important than any individual thing we got to do. Now, so hopefully you guys, so what we're going to do, we're obviously going to have a new chart. We're all excited about this. So we had the z-score chart, then we had the t-score chart, and we understand why that had to exist. And now, hopefully, I at least have shown you why this has to exist. I want to be able to say the same shit that I've said about means and percentages. I want to be able to do the same stuff with standard deviations themselves. But I can't use this picture because this picture is with one standard deviation that tells me how fat or skinny it is. And this is for every possible standard deviation. It's going to be a different shape. Okay, I like it. So, let me explain the process we're going to use. What we're actually going to do. Is this guy still going? Yeah. And then I've got this kind of sucks. I printed out so much stuff. I guess I just assumed I printed out the new chart, but I didn't. Sorry. Remember how we had multiple formulas to get to z-scores? And the reason that is so beautiful is I have the z-score chart. It doesn't depend on if I have means or percentages or whatever to start with. I just had to have a normal distribution. And once I convert that shit into z-scores, I can use the same chart. So that is one formula for chi-square. Just like this is one formula for z. And this is the best formula to start with, the idea of the shape. So now I'm going to show you the other formula that we're actually going to use. Period. Right? I don't think we have enough time to use that one. Right. So here is another formula for chi-square that uses that same, I call this the Jabba the Hutt distribution. Piece of the Hutt ate himself to death. I know. Goofy, and I don't care. Here's the other one, and this is for something called a goodness. Got it. And this is not something I invented myself. So let me give you an example before I even show you what the formula is, just so we can maybe see what the formula should be, and then see hopefully it's the same. I will be kind of pushing us in the right direction. So what this would be is, let's say I have, let's see I have 4 classrooms. And I expect that they all have the same number of students, right? You guys with me? So let's say I have 4 classrooms. I know there's 120 students. So I have 4 classrooms. I know there's a total of 120 students right now on this campus. It's a very small campus. I'm just starting this new college. I have one building with 4 classrooms and an office. And they're all full right now of not full, but they all have students in them. And I know there's 120 students there that day. If I expect that all the classes have the same amount of students, so it's a uniform distribution. So I'm going to call them classroom 1, 2, 3, 4, because I'm feeling very creative. What would I expect in each classroom? How many students? If I expect they all have the same number of students, each classroom would have 30. Okay, I like it. Sometimes people are a little mystified where that number came from, but hopefully it just makes immediate sense. 120 divided by 4, so 30 I would expect in each one. So what this test is, the reason it is called what it's called, is I want to see how well reality fits with expectation. That's what this test does. So if my expectation is they all have the same number of students in them, at the same time I kind of know I'm wrong, but I want to see how far off I am, right? So then I go and I observe. So E is expected, O is observed. It's amazing. And so let's say I observe in classroom number 1, there's 28 students. Classroom number 2, everybody loves that teacher. Classroom number 3, that poor teacher. Nobody likes that teacher. And then, let's see, 50, 63, 80. Oh, I got a whole bunch of them. What do I got in there? 37? Let's see if I did that right. 20, 40, 100, and 20. Yes. Yay, Jeff. What do you think the first step in this process should be, considering what it is I want to get a feel for? You could do it. Come on. What should be the first step I can immediately do right now with all these data values I have? All right, I plot them. It's not really going to be that.
Are we using that formula?
No. Yeah, I kind of gave it away whether we're not using it. That formula is a beautiful one to start with to describe why the shape is the way it is. But it's sort of like z-score like this. Now I'm talking about another chi-square formula. It uses the same Jabba the Hutt or piece of the Hutt distribution, right? Whichever one you like better.
Calculate observed minus expected.
Okay, you could look at the other side of that. But why does it make sense? I mean, when would I be perfectly right if all the differences were 0? So if I want to see how far off my guess is, the first good step would be see how far off each one is. Take the difference. So what's the observed minus the expected for each one of these? So this is 2. This is, let's do it for real, Jeff. This is -2. This is 5. This is -10. And this is 7. So now that we've, okay, be careful. We're not going to make this into the 5-step hypothesis test, but our conclusion will sound like the result of hypothesis test. And notice something about, let me take him away. Notice something about this picture. Where does it start? And why does it make sense it starts there? It starts at 0 because I can't have any negative stuff. Because the chi-square is based on things that are positive being squared. Holy shit, it's like positive twice over. Okay, stay with me. What? And now watch this. So if these were all 30, I would be 0 off. That means I would be right here. That would mean that that's like monster evidence that it's exactly, in fact, in this really silly little case, it's perfect evidence. We've proven it. Because I can see all the stuff. So, in order for me to show proof that I am really wrong, this is sort of, when you have an almost too simple situation, this is sort of like me saying, I bet you I can guess that person's age. And I'm like, they're 71. And they come over and they're like, I'm 70. Are you going to say, you're totally wrong? No, you're going to be like, holy shit, that's pretty good. So it's not enough evidence that I'm incapable of doing what I said I could, even though I didn't get their age exactly right. It's still freaking close. So it's still this idea of being far enough away to show evidence. So when am I going to have enough evidence that I'm wrong is if whatever I'm going to calculate is far enough away from 0. 0 would mean I'm exactly right. The further I get away from 0, the more wrong I am. So there's got to be some benchmark I can set that says, oh, if you go past this, you're just wrong. So if I said that person's 71 and they came over and they said, I'm 30, I'm like, I'm sorry. What kind of life have you had? But that would be monster evidence right there that I'm full of shit. But where's the line? What if they said they were 68? That's still pretty good. What if they said they're 60? Well, that's getting pretty far away from 71. So there's got to be a line I can draw that says, okay, you're so far off that you're wrong. So to calculate this, this should feel a lot like when we did standard deviation. What do you think I should do next, considering that these values, what do they all add up to be right now? This should kind of make sense. They all add up to be 0. That happened to us with standard deviations. I don't know if you guys remember that. So obviously what I should do is to do the same thing we did before. Square these. So 4, 25, 100, 49. Now let me ask you this. This first room, would you say that guess was really good? Yeah, right? I'm only off by 2. With me? What if this was 3 and this was 1, though? I'm still only off by 2, but that's relatively a pretty big difference. This idea of how relatively off it is. So that's why it makes sense. The last step in constructing the chi-square score for this situation. If you've looked in the back of your... Oh, I always make this too small. Get in. Now I'm not giving myself enough room. If you look on the back of that sheet, where's that sheet? There it is. So I really need one more column here. Observed minus expected squared divided by expected to give it kind of a relative, how relatively far off was I? Really kind of, this formula is never going to make perfect sense to us, but I want it to feel like it's kind of related to stuff we've done before. how relatively big is the difference? That's what we're kind of going towards. I have to square because some of these stupid things are negative. I want to divide by e to get a relative difference. So somebody said, guess how many people are over there? And I say 5, and there's actually 2. But if I'm like, guess how many people? I'm like 3,000, and there's actually 2,998. In both cases, I was off by, 2,999. I was off by 3, right? But the one with 3,000 is more impressive. Damn, you're only off by 3. But the other was like, damn, you were off by 3, dude. There's only 2 people over there. What the hell? How many fingers am I holding? Maybe. That's why I divide by e to see how relatively impressive this is. So let's see, what do I get here? Oh, this is going to be kind of gross, but you bet. 4 divided by 30, whatever that is.
You just add up all the OE squares and then just divide at the same time by 8.
So what's this formula require? Cover up the sum symbol. I need a bunch of those so that I can add them up. Now, to be honest, you could kind of play with that a bit, because it's just algebra, right? But let's finish this sucker out. There are others, and I love you, Jacob. You're always like, can I do it this way? Totally, do it that way. I love it. I'm going to show the textbook method, and then you can do it. But it's just algebra. I can factor that e out. Got to be careful, though. In this case, it works because e is the same for all of them. E will not always be the same.
E won't always be the same for every category.
That's right. Why was this one the same? Because my assumption was it was uniform distribution. Will that always be the assumption? No. So like grades in a class, I would expect fewer A's, more B's, more C's, less D's, less F's, right? So I would expect it to be a bell shape. Okay. So somebody help me out, please, dear God. What's 4 divided by 30? It's 2 divided by 15. That doesn't really help me out. Oh, 0.133. And then 25 divided by 30. Yeah. All right. And then 100 divided by 30. Yeah, 3.33. And then 49 divided by 30. 1.6 and then a bunch of 3s. All right. So if you add those up, let's see what we get. Because that's what the formula says to do. .3, 5.9, yeah, sounds about right. 5.9 what? Okay, now. This is the point where I want you guys to realize the thing we're missing to complete this test is that benchmark to compare this to. In order to get the benchmark, I need the chart. Right? Where did we get the benchmarks for hypothesis tests and so forth from the T-score chart or the Z-score chart? Right? So I'm going to have to run back to my office, print these out. But in the meantime, if you'll look at this other side, I've got number 1 done for you. I want you to go ahead and start trying to do number 2. Number 2 is different than this one. I want to see if you guys can figure out. All the expected stuff is not going to be the same. Because here I expect 20% to have less than 130 cholesterol level. So forth. All right, so let me go print that out and come back and see how we're doing.